Hello everyone. Today we're going to start going over the math and equations used in special relativity. In the last video, we covered some of the conceptual ideas in special relativity, with the key takeaway being that time flows differently depending on how fast you go. Relativistic effects cause measurements like time and length to change as objects approach the speed of light. But how do we actually quantify these effects? Well, we use the Lorentz factor, given by a lowercase gamma, to find how much these measurements will change. The Lorentz factor is equal to 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. So if an object is moving slow, the Lorentz factor has a value of pretty much 1, and this basically means that the object is not relativistic and will behave classically. Now, for the dilation of time, the time a slower observer measures is equal to the time measured in the faster object's frame, multiplied by the Lorentz factor. Since the Lorentz factor is always greater than or equal to 1, this means objects moving faster will always have time pass slower compared to an observer with less velocity. Let's go over an example of time dilation. Bob is stationary, while Alice is moving at 60% the speed of light relative to Bob. If Alice measures that it takes her 10 seconds to tie her shoe, how long does it take according to Bob? Let's start by writing down the time dilation formula. And we can write down that it took 10 seconds in Alice's reference frame. Now let's calculate the Lorentz factor. Since Alice is moving at 60% the speed of light relative to Bob, the Lorentz factor is 1 divided by the square root of 1 minus 0.6 squared, giving us the value of 1.25. Now we can put all our values into the time dilation equation, and we get that the time Bob measures is 1.25 multiplied by 10 seconds, which gives us 12.5 seconds. So to formally answer the question, Bob measures that it takes Alice 12.5 seconds to tie her shoe. Now let's talk about length contraction. In an observer's reference frame, objects that are moving near the speed of light will appear to be contracted or shortened in the direction of their motion. The contracted length is equal to the length of the object when it's at rest, or the proper length, divided by the Lorentz factor. Let's look at an example of length contraction. Bob is stationary, while Alice is moving at 60% the speed of light relative to Bob along the x-axis. Alice is traveling on a spaceship that she measures to be 10 meters long in the x direction. How long is the spaceship according to Bob? Let's start by writing down the formula for length contraction. And by reading the question, we know that the rest length is 10 meters, since in Alice's frame, she measures the spaceship to be 10 meters. Then solving for the Lorentz factor, we get 1 divided by the square root of 1 minus 0.6 squared, which equals 1.25. Then putting in these values into the length contraction formula, we get that the contracted length is equal to 10 meters divided by 1.25, which equals 8 meters. So to formally answer the question, we write down that Bob measures the spaceship to be 8 meters long. For our last topic in this video, let's go over Lorentz transformations. Since measurements like time and length change with relativistic effects, we need a new set of equations to switch between reference frames. The Lorentz transformations do just this. They allow us to find the time and position of events in a different frame of reference. The inverse Lorentz transformation lets us switch coordinates back to the initial rest frame. Now let's go over an example of Lorentz transformations. In frame S, Bob is sitting stationary on Earth while Alice is moving with a constant velocity of 80% the speed of light, relative to Bob along the x-axis. Alice passes Bob at time equals 0 and position equals 0. This is known as event A. Then 2 seconds later, Bob sees a tree at x equals 50 meters, gets struck by lightning. This is known as event B. According to Alice, what time and position does event B happen? Let's start by writing down the Lorentz transformations and factor equations. Then we can calculate the Lorentz factor. In this case, is equal to 1 divided by the square root of 1 minus 0.8 squared, which equals about 1.667. Next, let's write down the coordinates of event B in Bob's reference frame. The question tells us that it happens at 2 seconds and 50 meters. Now we can plug in our values into the Lorentz transformation equations. For the time coordinate, we get that Alice measures the time to be 3.334 seconds. And now we can solve for the position coordinate. Plugging our values into the Lorentz transformation for the position coordinate, we get that Alice measures the position of event B at negative 8 times 10 to the 8 meters. Lastly, let's clean up our answer by writing it in coordinate notation. So that's everything for this video. Thank you for watching.